Hello everybody, this is Yousef Siyabi. In this final update, I'm going to talk about self-healing copolymers. And before I start, I would like to thank my collaborators from Thomas's group, Dr. Ned Thomas, Vivek Subramanian, and also Zin Zhang. And also I would like to thank my sponsors, the online RU program at Texas A&M University. Self-healing copolymers actually exist for a sustainable future because there are smart materials that have that capability to repair themselves from physical damages. Self-healing polymers are sustainable, environmental friendly, and also need less efforts. And there are many applications of these materials, including coating, tissue adhesives, solar cells, and also many other applications. The main goal of this presentation is to understand the self-healing behavior of polymers and also learn how to measure the self-healing efficiency of these polymers. So first, let's define polymers. Polymers are formed when two or more types of monomers covalently linked and form plugs of repeating units. So for example, here, as you can see here, we have a diplug because it consists of two plugs, A and B, that are repeating along the polymer. Also, we can see here the triplug because it consists of three plugs, A, B, and then A. Also, this is called the alternating plug, and also there are many other types of plugs. So, in order for us to understand the self-healing behavior of plug polymers, we need to know what are the parameters that affect the self-healing ability of these materials from going from this state, which is the cut state, to the healed state. So the first one is the hard to soft plug ratio, and that actually affect the glass transition temperature and also the viscoelasticity behavior of the material. Also the self-healing temperature, what's the ambient temperature that we are testing the material in. The self-healing time, how much do we wait the material to self-heal. Also the bond type, which is also can be affected by the type of cross-linker. So how can we test the self-healing behavior of plug polymers? This actually depends on the type of deformation that's being made on the material. So if it's a scratch, for example, we are going to use a micro scratch testing, and that actually a device that causes a scratch on the sample at a specific load, velocity, and also scratch width. And if it's a cut, we're going to use tensile testing, and in which this actually stretches the sample over a range of stress, strain, temperature, and also time. In self-healing of scratches, the self-healing efficiency can be found easily by first scanning the area before the self-healing process starts, and then we need to measure the area after the self-healing process done, and from that we can use this equation to find the scratch healing of the material. In self-healing of cuts, we are going to use the dynamic mechanical analyzer, which actually measures the mechanical properties of the sample as it deforms over a range of stress, strain, temperature, and also time. As we can see here, there are actually many tests that can be run using this dynamic mechanical analyzer, and to measure the self-healing behavior of the plug polymers, we are going to focus on tensile testing. So what can we study using tensile testing? We can study the viscoelastic properties of the material by knowing the storage modulus, which actually describes the elastic behavior of the material, loss modulus, which actually describes the viscose behavior, and also the glass transition temperature. So in fact, viscose or viscoelastic word consists of two words, the viscose and also elastic. Viscose stands for liquid. If the material is 100% viscose, that means it's just a liquid. If the material is 100% elastic, that means it's a solid material. And also using tensile testing, we can study the physical properties of the materials, including the stress relaxation behavior and also the healing behavior of the material. So how can we measure the storage and loss modulus of the material using tensile testing? We first apply force that's alternating, and then we find stress and strain plots, and by comparing these plots we can find the phase angle that actually help us understand the viscous or viscoelastic behavior of the material. So if this angle is 0, that means the material is 100% elastic. So that means if we actually like cosine 0 here is equal to 1, that means the storage modulus is a maximum. That means it's 100% elastic. If the phase angle is equal to 90, that means cosine 90 is 0, which means that the storage modulus is at its minimum, which is 0. That means the material is 100% viscose material. And then we can also find the loss factor, which is the tangent of the phase angle. So the reason why storage modulus, loss modulus, and also loss factor are important is that because they can help us and determine the glass transition temperature of the material. So let's take polylactide as an example. As you can see here, they plot the storage modulus, loss modulus, and also the tangent of the phase angle, and then they determine the glass transition temperature at the glass transition region, which happens at around 70 degrees Celsius. And that's the glass transition temperature of the material. So what's going on at the glass transition range before the glass transition temperature and also after the glass transition temperature? So before the glass transition temperature, we are at the glassy state. That means the molecular chains of the polymer are frozen in place and behave like solid glass. Polymers are hard and brittle like a glass due to the lack of mobility. And after the glass transition temperature here, we are at the rubbery state, and above that TG, polymers are soft and flexible like rubber, and the mobility of the chains increases. So how can we determine the self-healing efficiency using tensile testing? We can do that by plotting stress versus strain plot for the uncut material. That means we are stretching the material until it is cut apart, and then we're going to compare this curve to the cut material. So first we're going to cut the material and then allow it to self-heal for a certain time, and after that we actually stretch the material using tensile testing, and then we obtain the plot of that, and then we compare the first plot to the second plot. So for example, in this experiment here, they actually obtain, so after 18 hours of self-healing, they obtain the self-healing efficiency to be around 90% self-healing. Here are the main results that were obtained, which shows the polymer and also the parameters that affect the self-healing and also the self-healing efficiency. Of course, we cannot compare all of these because the different, because of different testing methods for each one. However, we can, for example, compare these two, in which they use the same material, almost same conditions, however, different cross-linker, which actually shows that manganese chloride shows better self-healing efficiency because it requires less time here and also less self-healing temperature to reach 100% efficiency in comparison to the other cross-linker. And I think you can see here also different reactions. We have the metal legend bond type, also we have hydrogen bonding, we have irreversible covalent bonds and diol-alder reactions. We can compare these two since they are the same. These are the same materials. However, in the first one they used a cross-linker, and the second one they didn't use cross-linker, and that actually affects the self-healing efficiency. As you can see here, the first one has 90% efficiency, and the other one has around 15% efficiency. At the same time, same temperature, Same, also hard versus block ratio, and same test. This slide shows the references for each polymer in the results site. In conclusion, block copolymers are able to self-heal scratches and cuts, and the self-healing efficiency depends on several parameters such as hard versus soft ratio, time, temperature, and also bond type. And in order to understand the self-healing behavior of block copolymers, we need to understand the viscoelastic behavior of the sample. And thank you for listening.